talk is really going to be trying to identify some paradigms for the use of robots in architecture and also some perspectives. And I'll be doing that through the work of our research unit, Cita. So this is the structure of the talk. I'll introduce Cita, tell you a little bit about our research agenda. Then we'll enter into the paradigm of robots and fabrication as one of these paradigms in architecture. And then look at the second paradigm, which is the idea that robots are actually part of the architecture. And then, having identified these two paradigms, I'd like to talk about a project that we're involved in, an EU-funded project called Flora Robotica, which I think points to some interesting notions of possible convergence between these two paradigms. So that's going to be the sequence. So Cita. Cita stands for the Centre for IT, Information Technology and Architecture. We are now 11 years old. It was founded by Professor Mette Ramsgaard-Thomsen, and for the first year, she was the only member. We're now about 20 strong, and that group consists of approximately 8 PhDs, 4 lead researchers, so that would be Professor Mette Ramsgaard-Thomsen, Martin Tanker, Paul Nicholas and myself, and then we have a number of research assistants and also interns. Our key focus is to look at the productive intersection between digital technologies and architecture. We see the introduction of digital technologies as a fundamental research question, and we see it as not replacing existing methods of architectural investigation, but supplementing them, enriching them. Digital practice really enriches the ways in which we can draw, the ways in which we communicate, and also the ways in which we fabricate and build architecture. And this has real tangible results in terms of both the practice of architecture, the way we conduct architecture, but also in terms of the built environment that ends up being produced. At Cita, we are very much interested in the relationship between digital technologies and material practice. And so our research is conducted using a methodology of research by design, which is project-led, practice-based, and leads to the production of full-scale demonstrators. So, as I said, the relationship between the drawing and the artifact, the made artifact, really sets up the tradition of architecture. And this is one of the things that we're investigating, how it is, firstly, that these new methods of drawing, the programmed drawing, the computer-based drawing, starts to offer us new perspectives on material. How it allows us to interface with new types of technology of fabrication, how it allows us to address differences in scale, and how it is that those methods of representation actually begin to leave imprints in the physical artifacts that we're producing. One of the interesting things here, and I think similar to some of the work that we've just seen from Sven, is that quite often, because we're dealing with new methods of representation, we have to understand the thing that we want to represent in the first instance. And so our practice isn't necessarily representationally led, but actually we begin quite often with the making of physical material artifacts to begin to understand their behavior and understand the qualities, the dynamics, the structural behaviors of these systems to be able to represent them. And so this is really where we begin to describe this idea of a material practice. Our research is also very much interested in collaboration. Collaboration across academic institutions, collaborations with practice, collaborations with industry. Here we have the project Dermoid, which was a collaboration with Professor Mark Burry and his research team at Scalar, based in Melbourne. So that gives you a little introduction into what it is that we do at Cita. And now I'd like to begin to talk about this first paradigm about the notion of robotics related to the fabrication of architecture. So here we have an image, the Hyundai assembly line, and I think this really kind of shows, on one level, an incredible space of resource, but on the other level, a tremendously, I find, quite banal use of the world of the robot, in that we understand that the robots here are really making fully predetermined artifacts. And we're very much interested in how it is that enlisting robotics might allow us into more experimental spaces. To contextualize this, to nuance that paradigm of robotics simply on the assembly line and as fabrication tools, we can look to this notion of the yardstick for automation, which was described by Amber and Amber in their book Anatomy of Automation from 1962. What's really interesting about their analysis is that they are offering an understanding about how it is that machining operations are being embedded into machines, and there are very clear orders of automation that can be described. The first three orders are actually related to the notion of effort, the notion of putting energy into things. So we see that really all that's happening is that the replacement is simply muscular effort. We're not getting really any change in the nature of what it is that the tools are producing. But as we start to engage in orders 3 and above, we start to see that rather than having cracked the nut of effort, now the orders are beginning to deal with the notion of information. So this kind of sets the context, because really, in terms of our relationship to robots, the key question is a representational one. How it is that we can produce the information to be able to instruct the robot to make the artifact. So here in the project Stress Skins, which is a sub-project of our complex modelling research project, this particular project being led by Paul Nicholas, we have an investigation into how it is that toolpath generation can be informed by an understanding of multi-scalar relationships, which are investigated through simulation. What we mean by multi-scalar relationships is that we're creating design spaces that understand the behaviors of material. They can relate those to sub-elements, such as the panel, and then this can be projected into an understanding of the behavior of the whole. And the key issue here is actually about how we establish feedback loops between those scales, so that we can engage in a designerly activity within any one of those scales and begin to understand the implications. And then, through that model, be able to instruct the machine. Another project here, Filigree Robotics, being led by Martin Tamke, and also a collaboration with the Academy's Superform Lab, is looking at how we can be using clay to be able to create artifacts on unknown terrains. So here we have an examination of just exploring the extruder that's squirting out this clay to be able to create particular kinds of form. But the interest here becomes the idea of the flexible model, where we can be defining a series of toolpaths, but then allowing an unknown base to be introduced, which is then scanned using a laser scanner, and begins to literally digitally mould the tool paths prior to construction. And so we start to have this idea that we're dealing with a method of fabrication that isn't fully predetermined in advance, but starts to become a little bit soft and flexible to the conditions that are found. This idea that the tool path is actually informed by the site without knowing the site in advance. In our InnoChain project, which is an EU-funded Marie Curie PhD network supporting, I think, 15 PhDs across a range of academic and industrial partners across Europe, we have an interest in exploring glue, laminated timber, and robotic fabrication of these glue lams as well as their assembly. What's of real interest here is how it is that we can begin to incorporate understandings of material behaviour in the forming process as a way of being able to adapt tool paths. So we have the first passes of movement across the glue lam. As we all know, with wood, it is actually anisotropic. And so what that means is that it begins to behave in quite different ways, ways that are not necessarily fully predictable. And as we remove material, we release tensions. And this creates a source of uncertainty in what it is that we're producing. And so here, Tom in particular is looking at methods of optical verification to be able to adapt a tool path relative to the performance of the wood as it's actually being fabricated. And then in another complex modelling project, again led by Paul, this one called A Bridge Too Far, this is developing the work from the Stress Skins project, but starting to look at collaborative robotics. So what's interesting in these panels is in the prior panels they were using single point incremental forming but only addressed from one side. And here there are two robots now that allow the panel to be locally deformed on both sides of its initial plane. And essentially the deformations are all being informed through an analysis to be able to create zones of increased structure. So we see over here the two robots essentially mirroring each other through the material. And then finally, as a kind of step forward from the work that's been done in that particular project, and again understanding the way in which material behaves in forming, Paul is now starting to look at the ways in which there might be real-time adaptive forming, which is actually coupled to machine learning. So one of the key issues here is actually about material springback. As you're pushing down into a material to try and deform it, not all of that energy goes into the deformation, some of it gets released. And so that introduces inconsistencies, it introduces a world of tolerance. And the thinking here is that by using machine learning techniques, we might be able to create adaptive forming where the predefined model can start to be moved from, and the machine starts to be able to understand the forming actually in the context of fabrication. So really, to kind of return back to the yardstick for automation, we see really the context where Amber and Amber were in 1962, where they were starting to engage in this idea that machines were beginning to take on qualities of information, having cracked the nut of effort. And we see that the first there is the idea of self-feeding machines. Then we've got the idea of repeat cycles. and perhaps they were just beginning to engage in the idea of machine feedback. We fast forward to current trends, and we see that in the work that we've just been looking at, the notion of feedback is very, very much one that is fully engaged with. Automatic cognition is starting to be engaged with, and also the question of limited self, I can't actually read that there, limited self-programming is also now starting to be worked out. And what's interesting with their yardstick is they actually project that even further. So we see as we reach order 8, or order 7, the machine begins to relate cause and effect. Then we have originality, and finally it commands others. And one of the interesting things here, I think, in terms of beginning to deal with the idea of machines that can actually feed back, that are able to adapt through the actual process of making, as we begin to engage in this kind of notion of the craftsperson. But not only that, we actually begin to engage in a wider palette of materials, because if we understand a kind of history of modern machinery, we can also relate that to a development of the materials that are used by those machines, which tend towards materials that are homogeneous and are predictable in their forming. Once we begin to look at the idea that machines can adapt actually in the forming process, that opens up a whole new world of possible materials that might be able to be included within our architectural practice. So robots as architecture, really this comes out of investigations when I started in my postgraduate in Unit 14 at the Bartlett School of Architecture, where the agenda there was really to look at the possibilities of embedding computation into our built environment. And the focus was really not so much on the world of drawing representations, but in the world of actually making embodied artifacts that could actually engage us directly. Because of time, I'm going to move this forward, if it will let me. And in terms of perhaps some of the most immersive environments that are dealing with this idea of active spaces that embed notions of robotics within them, then perhaps the work of Philip Beasley is one to point to. And we've had a couple of very, very productive collaborations with him at Cita. I'll show this very briefly, where with the Sargasso cloud there was an aim to try and create a fully immersive environment, which I think was about 4 meters by 6 meters, that could engage a whole range of different scales of temporality and movement. In terms of these different layers, this kind of stratification, really dealing with a narrative of a form of an ecology, where you've got base layers that begin to generate energy, that begin to call layers above, and start to trigger these peristaltic forms of movement. And then more recently, earlier this year, a second collaboration where Philip was introducing to our students, master's level students, notion of curiosity-based learning in terms of these environments. So, I mean, just that was really to give a very brief overview of what I see as two of the principal paradigms within architecture. What's interesting is that they seem to be operating in fairly discrete trajectories at the moment. What's also interesting, I think, is that it also maps to perhaps a more broader cultural perspective, where we see robots operating at the level of utility, but also we see increasingly more into the world of experience and as we've seen today, very much involved in the world of performance, but perhaps also still in quite discrete silos. So could we imagine a convergence between these? The idea that perhaps fabrication is being included as part of the experience of an architecture, and that the robotics and their actions are also part of that architecture. So this takes us to the project Flora Robotica. And the aim of the project is really to investigate societies of symbiotic plant-robot biohybrids as social architectural artifacts. What essentially that means is we want to put plants and robots together and grow architecture. We're very fortunate in that the EU has funded us. It's a 4-year project. In terms of the targets for the project, architecture isn't really the dominant part of this. The dominant part is actually about trying to establish new foundations for the future of robotics and other artificial cognitive systems with clear progress beyond current capabilities and design concepts. We're currently about 1.5 years in, so what I'm going to be presenting is perhaps a little bit fragmented, but hopefully you'll see that there are some very clear trajectories of investigation that will converge towards the end of the project. These are the project partners: architecture and robotics, both in Copenhagen, computer science and the coordinator for the project in Paderborn, advanced mechatronics and environmental sensing in Stuttgart, molecular and cellular biology in Poland, and zoology in Graz. And so, just to start to get a little bit of a sense about what it is that plants are, what it is that plants do, and their temporalities, here we have a 3D laser scan taken over a series of, taken across a timeline, composited together to be able to create a 4-dimensional understanding of leaf foliation earlier this spring. There we start to see very, very clear attributes in terms of the idea of leaf coverage. As we move, in this particular one, we're starting to look at the idea of a spatial condition rather than just an object. So here, starting in mid-April, just outside our cafeteria at the Academy, and taken virtually on a 2-daily basis, we start to see the foliation and the change in canopy that occurs in this kind of spatial arrangement of 8 poplars. So we're dealing with entities that are in a condition of perpetual growth, that change between full canopy and complete exposure on a seasonal basis. And this sets up some very, very interesting challenges for us architecturally, where in architecture we tend to be more comfortable with material targets that are static, that behave predictably, and that can be turned to the kind of shapes and forms that we desire. And this project really is trying to challenge those design paradigms. So really, in terms of our vision, we're looking at an architecture that can be demonstrating adaptive growth that combines technical and organic, and that has a whole range of attributes in terms of guiding and anticipating, reacting and proposing over a timeline where we can be imagining a changing of architectural objectives that relate to both the scale, the structural capacity, and also other attributes of the system that's produced. And we see this as a cycle that is continually occurring. Was that the time?
That was like 5-6 minutes.
5-6 minutes, right. So in terms of one of the trajectories, we're of course focusing on the world of plants, and we're looking at ways in which we can be monitoring plants, looking at biomass sensing, looking at sap rate sensing, as well as a number of other parameters. We're also looking at ways in which we might be able to start to intervene in plants by changing some of the environmental conditions. Light is one of those ways. Changes in CO2 also is one of those ways. And we can actually use the plant as a sensor. So these are registrations of changes in CO2. As we see the big party of people emitting CO2 in that space, and we see that the plant is actually able to register that. And what's interesting for us, I think, as architects, is understanding perhaps where we started the project and imagining the plant as something relatively slow. We actually see that plants have very, very quick methods of being able to register and also adapt to their environment. We've also begun to look at interfacing the plant. Here we have our social media plant. It has its own Twitter account, and also through its movement, it's able to change attributes inside the room. So you can see here, I switched off the lights within 144 minutes. So this was based on a leaf that was open to light, and the light was being used as a way of guiding the movement of the leaf until it hit a trigger and was able then to switch the lights off in the room. Further work in terms of plants are also looking at steering and evolving environmental controllers. So here what we see is the growth of a bean, and up the top we see a light stimuli. This is described by the dot. And we see that depending on which one is switched, we're able to kind of change the trajectory of the plant. And as the plant matures, that shape starts to become more and more permanent. And so the idea here is that we might be able to define target shapes and for the controllers to evolve their behaviors to be able to achieve those. And part of that is also related to the motion tracking of plants, and using this as a way of being able to inform simulations and models of plants for us to be able to work with. In terms of the technical elements, we're looking at the logic of braided structures, and we've been trying to build a taxonomy of braids. I can pass this one around so you can have a little look and a little feel. The reason for choosing braids is that they're incredibly scalable. They're largely materially agnostic. As long as you can create your material in a fairly long fibre that has flexibility, you should be able to braid it. They're mechanically tunable. That can be done in many different ways through changes in topology or the introduction of other materials. They're actuatable, so particularly with this one, as you pull the small arms, you can see that they want to move. And so for our robotics partners, they see that as a tremendous potential. And they're also morphologically rich. So where in the previous taxonomy we were kind of dealing with perhaps a single bifurcation, when you start to deal with it in a larger system, and these elements are maybe 2.5 meters tall, we can see that we can create very, very morphologically rich structures. Not only rich in their morphology, but also able to be structurally supporting because we're throwing so much geometry at them. And one of the interesting things then is to be able to understand how it is that we might start to make these elements active. Plants might grow around them, they might grow in them. if they grow in them and they can move, as we can see with this one here. We can imagine a plant being able to be steered by this, but equally the plant actually affecting its behaviour. As a plant grows and it becomes more rigid, as it starts to build woody tissues, we would imagine that this would not be able to move to the same degrees anymore, and therefore it would require a need to be able to evolve its control. So we're looking at the idea of embodied evolution as a way of continually adapting the behaviours of our braided elements. So this is where we get to the idea of a braid, particularly this little one here, where we demonstrate, at the moment this is only demonstrating the motorized movement of this, but we can see that with some sensing on this, we could anticipate that this could be able to turn to target, and also perhaps deliver resources. So we see here that in this particular case, it's a watering effort, and what's happening is perhaps it's trying to find out where the plants are. We're dealing with a distributed system that's operating off low-level rules, so we don't want any centralized control, and so we imagine our plants actually having sensors that are delivering that information back into a network that allows the system to be able to learn and adapt over time. So almost finished. One of the kind of key understandings here is not to understand our braided structures as the robot, but actually in keeping with this kind of idea of low-level decentralized control, to actually consider one of the strips as the robotic element. So that would mean that any one of these braided structures is already becoming a swarm of robots. So that deals with the idea of the kind of active robotic element, but where do we have kind of robotic fabrication in this? So this is where we're starting to look at the idea of autonomous swarm braiders that might be able to make these or similar kinds of structures. This is our very first attempt, close to a year ago now, where we have an arena and we have material attached to the robots and they're moving around, and they actually did produce a braid, but it was very, very unstructured. This is the second iteration, and I think this one kind of shows some real promise. I could show you the actual movie of this. It's on the project website, flororobotica.eu. Please go and have a look. What I think is promising about this is that we've got the benefits of the autonomous robot, but we also have, in a way, the architect's specification. So we've got a kind of high-level descriptor, which is described by the line, and we can imagine technologies where that line might actually be able to change in real time, so that we can be producing all sorts of different braid features. So I think we're onto some really interesting territory with this particular technology. So really, that kind of marks the end of the talk. I hope that's given a little bit of insight into our project. Please have a look at the website, and please keep viewing what it is that we're doing on the project over the next 2.5 years. Thank you for your attention.